everybody, and welcome to the Introduction to Zero Net Energy Homes webinar. All attendees are in listen-only mode, and we'll start the presentation in just a moment. Waiting for a few more people to arrive. Along the way, if you have any questions, please type it into the questions area of your GoToWebinar panel, and we'll address it either during the presentation or afterwards. In a couple minutes, I'll be turning this over to Jamie. In the meantime, we'd like to take a quick poll just to kind of see where the audience is at. So if you would, take a moment and select the category that fits you the best. So the question is, please describe your experience with zero net energy or near zero energy projects. Are you just getting familiar? Are you familiar with the concept but not involved in any projects? Have you been involved with 1 to 10 projects, or have you been very active and involved with greater than 10? Oh, the results are coming in. We'll give it a few seconds. People are still arriving. We'll get the poll results, and then we'll go ahead and get started. All right, so it looks like most people are familiar with the concept but have not actually been working on projects. That's 61%. Second is 32% just getting familiar with the concept. And we have 7% of the people that have been actively involved with 1 to 10, but nobody yet has been involved with over 10. So I think a good mix and definitely a jumping off point for an introductory webinar. So I'm going to go ahead and close the poll. Hopefully y'all can see the results there. And then at this time, I'm going to go ahead and turn it over to Jamie.
All right, thanks, Erica.
You're welcome.
Self set up here. Okay, well, let's get started from the beginning here. So thanks for responding to that poll, and thank you everybody for spending part of your day with us to go through this overview and this introduction to zero net energy homes and opportunities to leverage high performance, high efficiency propane systems in those projects. For those of you who are interested, you're probably already aware that this course today is registered with AIA and GBCI and is eligible for continuing education credits. So those will be administered by PERC at the conclusion of today's session. As you might expect, the material here is copyrighted. So let's talk through the course description just to get everybody oriented here. Sort of as Erica alluded to, this is a jumping off course to get us more familiar with the idea and the concept of what is a residential zero net energy type home, and give designers a sense of what are the key issues and strategies for pursuing these types of projects. This course will go into the definitions of zero and what some of the implications of those definitions might look like. We'll talk a little bit about the current housing market of ZNE homes in the U.S. We'll spend a bit more time on the general design approach from a design and a building standpoint. What's the general philosophy towards approaching a zero net energy project? And then along the way, we'll look at some examples and opportunities to integrate mixed fuel designs into ZNE projects. So just so you don't get too bored right out of the gate, we'll just quickly jump through the objectives because they really mirror what we just described in the course overview. Let's start off with a quick introduction then. What is a zero net energy home? And just so you're aware, we might call it a zero net energy home, we might call it a ZNE. And even the term even goes by different names beyond that. It might be a zero energy home without the word net in there. Zero energy building typically would mean more of a commercial setting. So we're going to be more in the residential space with zero energy homes. And at a very basic level, what we're talking about is a home that produces as much energy as it consumes. And typically that production comes through an on-site PV system like the one that we show here on this basic house. And as a starting point, that's a good starting point, but like most things, it gets more detailed and a little more nuanced and a little more complicated from there. As I mentioned, zero net energy can go by some different terms. There's certainly varying definitions, which we'll look at in a minute, because the definitions certainly have some implications for how we communicate a zero net energy project. And then finally, this third bullet, we'll talk more about this in the design section, but a whole building approach is really critical. Most designers and builders would agree that we want to have an integrated design approach to zero energy projects where we're looking at everything together in an integrated manner. So it's the envelope, it's the mechanical systems, it's the lighting, it's the appliances, and then perhaps it's adding renewables. Looking at all those together so we can make good integrated design decisions. So we'll start off with the first definition, probably the most common. A zero net energy home is a home where we're measuring the energy consumption at the house, and that energy consumption is equal to the energy that's produced by the home's renewable energy system. Typically, this is over an annual cycle. So this definition is often called site energy because, as you can infer, we're measuring the energy into the building at the site. So if we're talking electricity, we're measuring the electric input through the meter. Natural gas, same thing, the natural gas input to the home through the meter. If we're talking about propane, we would look at the deliveries of propane to the home storage tank, and that would be the energy input from that energy source. One issue to consider when we're using this site energy definition for net zero is that site energy doesn't really account for upstream losses, upstream inefficiencies that are inherent to different energy sources. So we'll talk more about that in a minute. And then another consideration is that a given home may or may not be well suited for on-site renewables. And typically we're talking on-site PV when we say on-site renewables. There's lots of homes out there that have significant shading. They might have limited roof area compared to the amount of power that they need to generate. So issues like this, if we're strictly allowing a definition of zero energy that requires on-site energy to offset the home's use, they would preclude those projects from achieving zero net performance. But on the other hand, it is possible for a homeowner to purchase renewable energy credits from a utility or some sort of third-party source, and those renewable energy credits could indeed offset the home's energy use. So that's another sort of detail to look at in how we're defining zero energy performance in a home. So we just talked about a site definition for energy. Another form of zero net energy definition looks at quote-unquote source energy by starting further upstream from the house at the energy sources. So using this kind of a perspective will capture issues like losses and inefficiencies in the processing of natural gas or propane, for example. Or if we're talking about electricity, a source energy perspective is going to capture the energy that's associated with extracting and processing the fuel for the electric generation, and it'll also capture the inefficiencies that happen in the electric generation process along with transmission and distribution to ultimately get that power down to the house. So a key benefit of considering home energy use from the source perspective is that it's looking upstream. It's capturing the overall resource efficiency of the home more completely and recognizing the energy systems in that regard. At the same time, source energy, or sometimes we'll call it a full fuel cycle perspective, can be a little more challenging to relate, especially to a layperson who's not really steeped in energy systems and some of this terminology. And it's also important to really sort of understand the details as to how source energy is being calculated, because it will vary. It'll vary depending on the nature of the electric generation facilities that we're considering. Are we looking at the state level? Are we looking at the regional level, the national level, or maybe the utility service area level? all those different boundaries will capture different types of electric generation facilities, some of which may be more or less efficient than others. So the details certainly matter. Continuing on with source energy, again, it can also be called full fuel cycle. It's looking upstream and taking into account the extraction, the processing of primary fuels for power generation, along with the downstream losses with generation, transmission, and distribution. And then if we're talking about natural gas or propane, there still are upstream losses from processing, extraction, and distribution of those fuels. And because source energy does have this more comprehensive perspective on the resource efficiency of an energy source, it is used out there. It's used in programs like EPA's Energy Star for Commercial Buildings program. And on the commercial side, for the Department of Energy, they, about 2 years ago, released a common definition for zero energy buildings, not homes, but buildings. And that definition also relies on source energy as the metric for calculating energy use and net zero performance of buildings. So what these source energy factors sort of look like is showed here with some basic source energy factors for some of the most common energy sources that you might expect. So for example, if we look at electricity, a good way to think of this is for every unit of electricity that's used at the site, just over 3 units of source energy go into the electric process in the form of a primary fuel such as natural gas, coal, et cetera, to generate and deliver that electricity. For propane, we need 1.15 units at the source to get that 1 unit of energy delivered to the home, accounting for some of the upstream inefficiencies and losses from processing. Natural gas is quite close to that value at 1.09. And as I mentioned, the source energy factors, especially on the electric side, they will vary. They're going to vary depending on the footprint that we're looking at, where that boundary is, what types of electric facilities we're looking at. Is it hydro, or is it a lot of older, less efficient fossil-fired plants, et cetera? And then they're also going to change over time. So it's important to note, these factors can migrate and shift over time, especially over longer chunks of time. For the factors that we're looking at here, the electricity factors are based on the average nationwide U.S. electric generation fuel mix based on a 2012 eGrid national plant level database. eGrid is an EPA database of power generation facilities and catalogs their environmental characteristics. And just in case you're wondering, that 2012 fuel mix picture included about 12% renewable generation facilities within that mix. And then lastly, I want to jump back to the definitions just a bit further. From a homeowner standpoint or a consumer, somebody not deeply in the energy industry, when they hear zero net energy, many people will equate that in their mind to a $0 bill. It sounds like that's what they should expect. So some projects, some designers, some builders may choose to aim for that target, but we want to understand the details of how likely it is that we're going to get there. And so to achieve this, the cost of the home's energy consumption, all the energy flowing into the house, would have to be completely offset by the value of energy that's produced at the home and then sold back to the grid through net metering. So obviously this could be attractive for homeowners from their perspective, but getting to that $0 bill can be challenging. In many, if not most cases, utilities will typically have some fixed account charges that will add to the bill and make it more difficult to zero out the dollars. And then if we have extreme weather periods, if we have residents just having more energy intensive habits, maybe it's a thermostat set point, maybe it's a lot of plug-in loads, the more energy the home's using because of the homeowner behavior, again, it makes it harder to zero out that bill at the end of the day. And then another real key factor is utility policies on net metering. Many utilities will cap the amount of electricity which can be sold back to the grid for a credit. They'll cap that amount to the amount of electricity that the home actually uses. So this can be a challenge for mixed fuel homes in particular, because they need to sell back quote unquote extra electricity to offset not only the electric use of the home, but the home's usage of gas or propane. So net metering policies are certainly relevant to reaching a $0 bill. And then one last point, in addition to the net metering policies and how much electricity can be sold back, the price points are also really critical. If a homeowner is buying its electricity at one price and selling it back from on-site generation at a lower price, again, that's one more challenge that's going to make it hard to be able to zero out that utility bill. So some of the factors to think about with that type of definition. One more option to at least be aware of is to design and build a home that is zero energy ready. So this can mean a less aggressive energy target. It may mean a very efficient home that does not include the on-site renewables. So that's an option that quite a few builders and designers in the industry are considering, and some are building to that. And those that are in this territory, as well as all the other definitions we looked at already, it's good to put a number on, how close are we to zero? Are we just a matter of adding 6 kilowatts of PV away from zero energy, or are we near zero? How do we measure that? And really, the industry standard for doing that measurement in the residential arena is this thing that we call the HERS index, and you can see a graphic of that here. So HERS stands for Home Energy Rating System Index, and it's kind of like this barometer. Lower is better, so it's a little bit more like golf. We have this thing called the standard home. If you look there, it's at 100, standard new home. It's benchmarked to a home that was built to 2006 Energy Code standards. So it's not quite so new, but still, that's the benchmark for the scale. It's at 100. As we go lower, we're getting more and more efficient. 1% more efficient for every increment we drop down the scale. And you can see all the way down there at zero. That's one definition for a zero energy home. And what we'll see in some examples in upcoming slides is that lots of homes can get down into the 50s, into the 40s, maybe even into the high 30s with just good, efficient design, reducing the loads. At that point, the momentum really sort of stalls out, and the next best investment that makes the most sense is likely renewables to drop the HERS down much further, closer to zero. HERS are very common in the industry now, with over 2 million homes having undergone a HERS rating in recent years. And really hundreds of new home builders each year now have most or all their homes get a HERS rating. So it's a pretty familiar metric within the industry. Looping back quickly to that concept of a zero energy ready home, designers and builders that are interested in that can take advantage of this U.S. Department of Energy program called DOE Zero Energy Ready Homes. So it's a voluntary program and label with requirements for both efficiency as well as performance. And that's an important sort of dual approach there, because more and more designers, more and more builders recognize if you just chase efficiency in the home's design, we might miss important provisions for indoor air quality, for comfort, for moisture protection, that make the home just less comfortable, less, a lower performing home to live in. And in addition, this DOE program also incorporates a few provisions to make the homes PV ready. So the homes can more easily add solar in the future if that's in the cards. So that was sort of a real quick tour through some of the definitions that are out there for zero. I'll point out we didn't cover the entire waterfront. There are other definitions out there. There's a concept called time-dependent valuation, TDV, which is used primarily in California, where the value of energy differs according to the time of day and the time of year. So not all energy is really equal, and it's weighed differently. So that's another way to do the energy accounting. And then there's also projects and programs which have a zero emissions goal. So not zero energy, zero emissions goal based on the overall composition of the energy used for a given home or given building. So those are also out there as well, just to be aware of. As far as which approach to use, as usual, it depends. If a design team or a builder is participating in a third-party program, maybe it's a utility program, maybe it's a program like the DOE Zero Energy Ready Home program, then the program is going to dictate how zero is defined and what the requirements are. So that's taken care of in that case. But it's also good to think about as design teams, builders, and their designers, and maybe their energy consultants look at this landscape. The metric that we use to define zero, whether it's site energy, whether it's source energy, whether it's a $0 bill, whether it's quote unquote near zero. Some builders will use a definition like that and just get a very low HERS score. Whatever the choice might be, it will have some implications. It'll have implications on the system choices that we might select for different applications in the home, and it'll certainly influence the messaging and the communication for that home. For example, we could have an identical home, but it's built to a $0 energy bill in one case, and it's built to a HERS index of 0 on another case. And you can imagine the messaging and the marketing and setting the consumer expectations would be very different between those two scenarios, even though it's the exact same home, and we might put the word 0 on it. So it's important to understand the implications in terms of messaging and communicating to buyers and clients. And then this last point, it's generally true, regardless of the way we're defining zero and the project goals. As you get closer and closer to that end goal, the remaining steps get a little tougher, they get a little more expensive. So that's something to keep in mind as well. Okay, so that's the definitions. Next, we want to take a quick look at the market of zero energy homes in the U.S. market and get a quick understanding of what that looks like. So to do that, we have a really useful resource called the Zero Energy Residential Building Study, and it's from a group called the Net Zero Energy Coalition. The report was just published last year in 2017. So to grab a few nuggets out of this, the report documents that there's over 4,000 zero energy buildings overall in the U.S. market, representing over 8,200 dwelling units at various stages of development back in 2016. And if we look at year-over-year growth, we can see that we had a 33% increase in the number of units from 2015 up to 2016. So that reinforces the idea that there's more interest, more growth in this market segment. As far as the building types that are involved, based again on the study by the coalition, just over half are multifamily units. And while the size of those multifamily projects varies quite a bit, the average, if we want to go there, is about 53 dwelling units for those projects. And on the other side of the coin, just under half the projects are single family in nature. And again, many of these projects are single residence, but there are some much larger developments in the mix, so the average project size ends up being around 44 homes. And as we look ahead at a few examples and I guess mini case studies, it's important to note that most of the technologies and certainly the design philosophy that we'll talk about really applies to both single family and multifamily in most cases. So where is all this activity occurring? You can see here by the graphic that the top 5 states are in the light blue, the darker states are in the top 6 through 10 states are in the darker blue. So in terms of location, California is the top state for zero energy projects with over 3,000 units, and that state also has the most zero energy builders. Some of the factors leading to California's role in this market segment are, first off, the energy code, often called Title 24 there, is fairly aggressive, so that raises the minimum bar, so that the gap between just building a very minimum code home to move to higher levels of performance is lessened. It's a big building industry there, so there's more activity, and there's generally fairly strong awareness and support of zero energy projects there. Massachusetts, over on the other side of the country, is the second state based on the number of zero energy units, and Vermont actually has the highest number of zero energy homes per capita. New York ranks fourth by the number of zero energy dwelling units and third in terms of the number of builders. So the coalition study also tried to characterize what level of energy performance did all these buildings actually achieve. And you can see that the majority of projects are considered to be zero energy ready. This threshold is often less costly to achieve, and can also be a stepping stone for builders and designers, that they understand what's involved in terms of design, in terms of economics, in terms of cost impacts, of really reducing the loads in the building and getting it to a point where on-site or off-site renewables could zero out the energy. So zero energy ready is a common sort of landing zone at this point. The graphic also shows that the share of projects which actually achieved zero energy performance increased from 9%, that's that light blue slice, all the way up to 23% the following year in 2016. And then net producers. This is a pretty remarkable little segment. These homes produce more energy than they use. They also increased from 2015 to 2016. That's the gray slice. So it was 6% of projects in 2015 and 8% of projects the following year. Looking forward, I think there's increasing sentiment in the industry that the momentum, the awareness, and the activity level in the zero energy or zero energy ready part of the market is increasing and could be approaching a tipping point. According to the coalition's assessment, nearly 30,000 zero energy projects are currently being planned. And really some of the underlying factors for this market growth is what I call often a toolkit, the number of technologies which are cost effective that can be utilized by the builders and designers in the envelope, in the mechanicals and lighting, appliances and renewables. It's a bigger and bigger toolkit that's available. And more builders and designers are familiar with how to leverage those tools in a very effective way. So that's a big factor. Another one is that minimum bar, the energy code, that's the worst home that can be built legally in a jurisdiction. That's getting better and better. So the gap between a minimum code home and higher levels of performance is narrowing. And then there's also just much greater awareness that zero is attainable. It used to be a real novelty to see a zero energy demonstration home maybe 10 years ago. That's really no longer the case, that there's many projects out there, so the awareness and the skill set of builders and designers has really increased. Okay, next we'll talk a little bit about the strategies to achieve zero net energy. And we won't do this in great detail, but we do want to look at sort of what's the most common design philosophy to pursue a home which will be zero energy or near zero or even zero energy ready. And I feel like there's pretty good consensus in the construction and design community about what's the playbook for how to get there. So really, this quote sums it up well. Energy efficiency is generally the most cost-effective strategy with the highest return on investment. So in most projects, the first place we want to look and start is the building envelope. And we'll start just with that first sub-bullet, the insulation quantity. So this is our value. How much insulation are we putting into the walls, the foundation, the roof system? And we'll look at some target levels here in a second. We also want to look at not just quantity, but also quality. So if an insulation job is done poorly, there's gaps, it's compressed, it's not well installed. Once those building cavities and assemblies are covered up, we've probably locked in a real derating of that efficiency for decades to come. So quality is really important along with quantity. And at the end of today's talk, we have a resources slide which includes something called the thermal bypass checklist, which is a good resource to help sort of have a checklist approach to a good insulation job. Third item on this list is the air sealing. I'm sure as most of us are familiar, this is a really cost-effective way to increase homes' efficiency. And we have a quick graphic here to show you. Pretty small probably, so I apologize for that, but the details aren't so important as the concept of, it's very well documented where homes leak. So the standard approach is make sure we're calling these out in design details, make sure they're built into scope of work documents for the trades, so all these different areas of concern are taken care of. Once we start doing that, air sealing becomes very methodical and we get a tight building. In terms of windows, that fourth bullet, windows are often a real weak link thermally in the building envelope compared to the walls and the other parts. So you see more and more high performance projects going with really good double pane windows and an increasing number going with triple pane glazing, especially if they're in a mixed climate or a cold climate where the return on that technology is even better. And the extent of windows also matters. So this is an area where a designer or maybe an energy consultant can do some energy modeling and show and understand what are the impacts of adding more and more glazing on the home's energy use and its loads, and trying to optimize that, because natural light is great and views are great, but the more glazing that's added, it's going to pull away from the efficiency of that envelope. So trying to optimize that relationship. And then the last bullet here is the home's orientation. This is another area where modeling can be really powerful. We can flip the home, different orientations, and as a result, the heating and cooling loads may change. If we're looking to add PV in the future, we want to make sure we have enough south-facing roof to accommodate that PV. So that's another factor of looking at the home's orientation. So that's the envelope in a nutshell. Those R values that I mentioned are shown here based on the Energy Code. This is the IECC, International Energy Conservation Code, 2015 edition. This is available online. And the R values that we see here for all the different parts of the envelope are for climate zones 4 and 5. You can see they kind of cut through the middle third of the country, a lot of mixed and colder climates. And there's different R values for the other zones that you see here on the map. So we won't spend much time looking at these actual values. Like an R49 ceiling, that's the attic insulation, R20 walls, or R13 walls, that's the cavity insulation, plus R5 exterior, like a 4x8 continuous foam board would be exterior of the wall, and the other R values there. But the key takeaway here is that this is really a starting point. This is code minimum. So high performance homes that are aiming for 0 or near 0, they'll often start here and build upon these to some extent. Again, using energy modeling to figure out what's the best investment. Is it worth putting more and more investment into the envelope, or is that money better spent elsewhere? And as far as the air leakage, I mentioned that we want to look at those details, put them in the construction docs, put them in the work scopes, and then the last key part of that is to measure. For those of you who may be familiar, there's this test called a blower door test, which a technician runs. It pressurizes the home, and it measures how leaky it is. We get this metric called an ACH 50 rating out of that test. Code actually requires that the value be no greater than these levels, so no greater than 5 if we're in climate zones 1 or 2, and so on down the line. And as you move to the right in this table, we get into these above code voluntary high performance programs, with the one on the far right being called Passive House, which has a really strong emphasis on the building envelope. And you can see here that the air leakage required by Passive House is less than 1 ACH 50, down at 0.6. So the expectation is clearly that code minimum is a fairly tight home, but we really want to go a little bit beyond that in the pursuit of higher performance projects. Okay, next is mechanical systems. So we've talked about the envelope. Really, the strategy there is a really good envelope, throttle down those loads as much as we possibly can. Now, for the loads that remain, we want to meet them with high performance, high efficiency equipment. So the first thing I'll talk about quickly is the ventilation. Just from that last slide, you can see how well air sealed these homes are going to be So it's no longer sort of an extra credit idea to have ventilation system. It's something that we need to have to ensure that there's enough fresh air coming into and out of the home and that we're diluting pollutants and odors and things like that. So this particular ventilation system is called a heat recovery ventilator. It pulls air into the home from outdoors while it exhausts stale air from inside to outside, and it lets those two air streams cross in a heat exchanger, so the fresh air coming in is tempered. It's not as cold in the winter. It's not as hot in the summer. So ventilation is really important. In terms of heating systems, some of the real sort of basic options and go-to options are going to be a high-performance furnace. We can have a high-efficiency heat pump, or we can even have hybrid heat pump furnace combos, which I'll talk about more in a few minutes. In terms of a furnace, from a designer standpoint, if there's a desire to spec a very high-efficiency furnace, you can do the homework, or else we can look simply to the spec released by Energy Star. It's called the most efficient, sort of like Energy Star Plus. And any qualifying furnace that earns this label will have a AFUE rating of 97, efficiency rating of 97 or greater. So that's a good go-to solution which is available. Cooling, again, we want high-efficiency cooling systems. And I call out two sub-bullets here. Sensible, that's reducing our temperature. But then the second part is also a really important consideration to think about: dehumidifying. So you might imagine our building envelope is really well insulated. It's really well air sealed now. So that maybe I used to turn on the air conditioning in my home in early April. But now, because that shell is so good, my thermostat isn't calling for cooling, but I still have humidity. Maybe it's from the outdoors, maybe it's from indoor sources. We want to have a good strategy to dehumidify the air so we're not stuck with high humidity levels, which can lead to mold and uncomfortable conditions. So the two main strategies to get at that humidity, one is just a standalone separate dehumidification system, and the other would be just a higher-end central cooling system which can operate not only based on a temperature setting, but also based on indoor humidity. So something to keep in mind on the mechanicals. And then I just popped up the water heating. Water heating has always been pretty significant in terms of home energy use. It matters even more now because we've really cranked down the heating and cooling energy. We've cranked down the loads. We're addressing those loads with very efficient equipment. So water heating now is proportionally a bigger consideration. Some of the go-tos there are high-efficiency propane or gas tankless units. We'll look at them a little bit more. Heat pump water heaters are an option, a bit more so in milder climates, where they can, the cool exhaust air can be put to a more productive use, and it's not a compromise for indoor comfort. High efficiency storage tanks, particularly natural gas or propane, can be used, and then hybrid systems, and we'll look at one or two examples of that in a minute as well. So that's the envelope, that's the mechanicals. Next in line, let's think about lighting and appliances. Sort of like the hot water, lighting and appliances have always mattered, but they matter more and more now because the heating and cooling loads are really being throttled down effectively. So we have really good options here for lighting. LEDs are almost a no-brainer at this point. We do call out Energy Star. So instead of just using any LED, Energy Star labeled LEDs have some extra assurances built in. They go through a whole battery of tests. For example, they look at the lumen maintenance, how well the light output keeps up over time. So we don't get stuck with a light that's efficient, but it fades too quickly and the consumer's not happy. Also on the control side, auto-off controls that kick off the lights once the space is vacant for a period of time, they can make a lot of sense in a basement or a closet where lights can be left on and we don't know it. So that's another option to think about. And then appliances, same kind of thing. We have a whole menu of Energy Star appliances, from the dishwasher, the fridge, the clothes washer. Energy Star now labels clothes dryers and even labels ceiling fans and bath fans. So across that whole suite of equipment, Energy Star equipment is just a good bet to specify and allows us to have more efficient equipment that's going to consume less power. And just like the LEDs, the Energy Star label, in many cases, it's energy, but it's also things like it's a sound rating for Energy Star bath fans, so they'll be more quiet, or it's water savings on an Energy Star dishwasher. So there's some extra performance benefits from using Energy Star appliances. And the last item we point out here is the energy monitoring and feedback devices. As most of you can imagine, the homeowner really matters in a high-performance home, the way they use the home, the way they consume energy. So there's a growing movement to let homeowners have more of a view into how the home is operating and what are the implications of how they're using it. So there's a lot of equipment out there that involves some basic metering set up at the home, and you might have a countertop display, or more likely now you'll have a smartphone app that gives you real-time energy use as well as historical data, so the homeowner can be more dialed in and understand their role in how the home is performing. And then last in this chain, we've really looked at the loads, we've looked at efficient equipment, and now we want to look at the renewables. If a project is aiming to use renewables to approach zero. So the most common renewable energy options include roof-mounted PV, like you see here on these townhouses. Some of the obvious factors to think about if we go there or not are the cost of the PV, obviously. What is the net metering policy that the homeowner would be operating under with their utility? And what's the buyback? What's the spread between energy bought and energy sold with the utility? So those can all influence the economics and how attractive it might be to incorporate PV into the home. And that's really very project specific. And then another option, just to mention, is the increasing ability to have on-site PV in conjunction with on-site battery storage. So in this type of a configuration, the battery can absorb and store energy that's generated by that rooftop PV, and then it stores it for the home's use at some point in the future. And with more advanced controls, it can really optimize when that home is going to draw on the battery and use energy. And if it's done well, it can really optimize the utility savings, the price savings for that homeowner. That's something that's really sort of emerging at this point, but I think we'll see a lot more of it. And then lastly, if a home just isn't a good candidate for solar, like we said earlier, we have those options for off-site renewables, which can be purchased and used to offset some or all of the home's energy use. Get a quick sip of water here. So next we're going to look at a trio of project examples, which are mixed fuel designs. So we'll start with this one in the Southwest, built fairly recently in 2012. It's just over 2,000 square feet. So the slide shows a sort of a selection of some of the high performance features that this home has. The advanced framing at 24 inches on center, so the studs are spaced more widely. That opens up more space to install insulation, and as the end result, we get a better thermal performance out of the wall. The home is very well air sealed, and it uses, for the ventilation system, an HRV unit, which we saw earlier, which is a very efficient form of ventilation for the house. In terms of mechanicals, the home has a 95% efficient propane tankless water heater. And based on the energy modeling for the house, it ended up at HERS 49. As I mentioned a few minutes ago, that's quite a good score. Typically in the low 50s, 40s, maybe even high 30s is where the efficiency and reducing the loads kind of stalls out, and the next best investment, if there is to be one, might be in on-site renewables. But lots of projects get to this point in a very economical way, and they achieve very good performance at that level. Next example is in the Northeast, larger home at 3,000 square feet, also built in 2012. The designer's goals for this project were very tight envelope and using very efficient systems for the home. And it was actually a rebuild where the previous structure was torn down all the way to the foundation and then rebuilt up from the slab, reusing some of the same construction materials along the way. There's ample daylight throughout the house provided by windows as well as solar tubes. A 90% efficient propane boiler satisfies domestic hot water and also serves as the source for an in-floor hydronic heating system. And that system is coupled up with a heat pump system that also provides space heating. For this house, the HERS score ended up at a HERS 39, and a PV system was contemplated and modeled and at 9 kilowatts. And if that were to be installed, the HERS score would drop down to a value of 2. That's a good example of very efficient equipment, good envelope, good mechanicals. And the HERS, we've gone about as far as we can with the HERS. And if and when solar would be added, the HERS score for this house would be right around that 0 mark at 2. And then a final example shown here, just under 2,000 square feet this time. And this home is a pretty good example, pretty unique example of a really robust building envelope with super insulated assemblies and really robust air sealing. So one key feature here that we'll look at is a double wall. So it sort of looks just like it sounds. We have an exterior 2x4 wall, you can see there, and then there's a gap between the studs, and then there's an interior 2x4 wall. And that gap does a couple things for us. It prevents the studs from being a thermal bridge from the outside to the inside because they're broken, there's a gap. And it also opens up more and more width, which is subsequently going to be filled with insulation. So as a result, in this project, they filled the entire width of that double wall with open cell spray foam to achieve an R45 wall assembly. And you might remember a few minutes ago, Climate Zone 5, which I believe is Massachusetts, code calls for an R20 wall. So this wall is more than double what code would be looking for in that regard. The attic was insulated to R67. Code would have called for R49. And the windows for the home are triple pane R5 windows. So really, a really well insulated envelope. And then the air sealing achieved less than 1 ACH50 on that blower door test. So again, that's, if you recall that slide, that's really getting down to the very well air sealed end of the spectrum. In terms of mechanicals, domestic hot water is provided by a high efficiency propane tankless water heater down in the basement. And the homeowner has been pleased with the output of that. They have a few kids in the home, and the water output has been more than enough. The project team had considered solar hot water, but the economics didn't really pencil for this case. So the HERS score with all of those features, the envelope, the really robust envelope, the mechanicals, is 34, which is quite low. And then on top of that, this project added a whopper of a PV system at 18 kilowatts, and incorporating that into the HERS rating, the value is actually negative. It's negative 21, and the home actually earns a credit from selling excess energy back onto the grid. And the excess electricity more than offsets the home's fairly modest propane usage, which is used for the tankless as well as for cooking. So this is an example of a mixed fuel net positive energy building. So on the heels of those examples, we'll look at some of the common design goals in net zero and near zero and zero ready project, and how mixed fuel designs can contribute to some of those design goals if they're in the mix for a given project. So they're listed here, and then we'll tick through them in the next few slides. First, cost savings on equipment, energy and energy cost savings, reduced emissions, and the ability to use hybrids. So in terms of first cost, it's sort of just a general example here. Typical home is going to have a much bigger heating load. I think we've kind of covered that ground with the emphasis on the building envelope. A near zero home, much smaller heating load. So if we're investing in a high performance but more expensive heating system, that's probably a pretty good payoff in a typical home, because we're running the heater a lot and we're going to save a lot of energy each year, so our payback would be expedited. And the reverse is true in that near zero home, because the heating load has been reduced so much, we're not really running the heating system all that frequently. It's not running that much, so we're not really leveraging that super high performance heating system. As a result, our payback is drawn out, it's stretched out. It's going to take longer to pay back that heating system. So perhaps the best example of this, based on some modeling which PERC did a few years ago, is shown here. Ground source heat pump systems, very, very efficient, but traditionally they've carried a significantly higher first cost. In this study, it was around $30K. And a more traditional, fairly high performance system with a 95% propane furnace with a pretty standard AC system, a little bit less than half that price. And the numbers will vary by project, and as a designer or builder, perhaps you've looked at these numbers, but the concept is simply that in a high performance project where the envelope is good, the loads are really reduced, it's worth a careful look at what's the next best investment to make. Is it in heating equipment, or might it be somewhere else in the project where you get more return on that investment? So that's one concept where a pretty good, pretty efficient, economical heating system could be a good fit for project goals. Another quick example is on the energy cost savings. So this chart that we see here is a bar chart looking at a whole menu of water heating systems. Anything in blue was a propane system. Again, this is a PERC study. Anything in red was an electric water heating system. And this is a moderate demand home, which was modeled in a mixed climate. So somewhere, climate zone 3, climate zone 4, kind of mixed heating, mixed cooling seasons. And sort of the trend is that lowest cost system is a propane condensing tankless system with a fairly low cost. It looks like it's in the low 200s. And by comparison, oops, I mean to jump there. By comparison, that system E is that very typical but not very efficient electric tank water heater, which is still in many, many homes. And the annual energy savings between those two is over $100. And even a heat pump water heater, which is still quite efficient, that system over on the right, there are some modest savings to be had in this study based on the tankless performance. And again, this is based on modeling using US DOE's BOP modeling software. So again, it's worth looking at some of the options, especially in the water heating arena, to see what systems can contribute the most towards reducing the energy costs. Next, we'll take a quick look at source energy savings. So this slide takes just a little bit of orientation. We're talking source energy here, and these factors that we see here in the bars, they relate how much energy does a home need for water heating in terms of its source energy, and each bar is a different kind of water heating system. Everything is benchmarked to this bar on the left as a value of 1. Everything is benchmarked to just a standard efficiency propane storage tank. Okay, so if we look at, again, that standard electric resistance tank, it has over double the source energy to provide hot water to that home compared to the benchmark of 1. If we consider a electric heat pump, it's way lower than that value of 2.07, but still a little bit higher because we're looking at source energy and the upstream implications of using electricity for the energy source. If we want to take a quick look at tankless, this is sort of an extension of the same charts. So we still have that benchmark of 1 over on the far left. If we want to look at tankless, we can see that a standard efficiency propane tankless, again, from a source energy standpoint, is a really good bet. It has very low source energy to provide water heating energy to this home, and sort of the best on the market tankless, which is a little more efficient, will have the lowest source energy factor at 0.72. So if source energy is in the mix, if it's part of the project goals, this kind of information is worth considering. And same kind of concept here, but we're looking at greenhouse gas emissions as opposed to source energy, but the concept is pretty similar. So we're benchmarking everything to that first system on the left, which is a value of 1 for the propane storage tank water heater. And in order to provide the hot water to this home across this different menu of heating or water heating systems, you can see that the best available electric storage tank system has a greenhouse gas emissions factor, which is going to be 67% higher than the benchmark. And by comparison, again, the propane tankless, it's a very efficient unit with very modest upstream source energy factors, so it comes out looking fairly good in terms of greenhouse gas ratio. And then quickly want to look at a hybrid solar hot water system with propane tankless backup. So this is the same slide we just looked at a minute ago with source energy ratios. Our benchmark is still 1, but this really tiny little bar here on the left is at 0.3. And the reason it's so low, it's a solar water heating system in a hybrid setup with propane storage tank as the backup. In most cases, we can't rely only on the solar hot water, so propane storage can be a backup companion. It's not going to operate as much, but the overall hybrid performance of that system is really, really strong at a value of 0.31. Again, these are all benchmarked to compare sort of an apples to apples across the different options that we see here on the chart. And again, the standard electric tank is way up there at a value of over 2. And then same systems here, but we're not talking source energy, we're talking greenhouse gas. Same sort of pattern emerges, that hybrid solar storage plus propane tank way, way lower than any of the systems at a value of 0.3. So the hybrid solar hot water plus a propane backup storage tank really shows strong performance compared to really any of the other options based on source energy and greenhouse gas ratios. And then one last hybrid system to think about and just consider is in the space heating realm. This is a modeling example which looked at a typical home relying on a heat pump, standard heat pump for heating and cooling. The energy costs are a little bit over $2,100 annually. If it's a high efficiency unit, the energy costs dip below $2,000. And then now if it's a high efficiency heat pump in a hybrid setup with a high efficiency propane furnace that takes over heating when the outdoor temp dips below a certain temperature, it's sort of the best of both worlds for those systems. The overall annual cost is much lower than the alternatives, and there likely is a small first cost bump to use that hybrid heat pump or that dual fuel system as it's called, but with saving $200–300 annually, that's made up for in a few years. So just summarizing some of the high-level points here. The zero net energy, near zero energy ready market is certainly growing. The awareness is growing, the number of projects is growing, the number of builders and designers participating is on the uptick. We talked a little bit about how we can define zero and really just being aware of the implications on communicating the project objectives, setting expectations, and selecting systems that support the project goals. Site versus source can be important on the project depending on how we're looking at zero. And then really from a designer standpoint, I think it's a really great time to be in this part of the market because that toolkit of options, whether it's different energy sources, whether it's different envelope technologies, mechanical systems, appliances, controls, even renewables, even battery storage, all that is a ever-growing toolkit of solutions which designers can use to meet their project goals. So I'm going to leave it on this slide momentarily while we take a look at the questions. This is the foreshadowed resources slide, which contains the link to the energy code and several other resources which we referenced here. directly or indirectly, which can provide a deeper dive in some of the topics that we've covered today. As I let you look at those, let me open up the question pane and see what we might want to do there. Okay, just a few questions it looks like. What is BTU per BTU? I believe that's going back several slides to the source energy factors, and it's conveying the BTUs of total overall source energy to get a BTU of energy to the site. And then we had one other comment on the map that Rhode Island was highlighted instead of Vermont. If that's the case, I apologize. We'll go back and correct that. Erica, any other questions that you fielded, maybe in the chat window?
I did not. Jesse?
No questions, just requests to receive the presentation, which I have sent. So if anyone is interested, please email me, Jesse, Jesse, period, Marcus, Marcus, at propane.com. And again, as a reminder, this presentation is also available on propanetrainingacademy.com as an on-demand CEU course. This is along with some other CEU courses that we've developed among the years. So please visit propanetrainingacademy.com as well.
Very good. We'll leave it with this slide with the websites in addition to the websites that Jesse mentioned. Thank you, everybody, for your time and participating in today's webinar.